Hi, my name's Tim McCoy. I'm the chair of the Department of Mineral Sciences and the curator in charge of the Meteorite collection. I've worked here a little under 69 Mercury years. There's a conversion for those of you that are sort of Earth-centric. And the title of my talk is the 160 milligram planet. Now, when you hear that, you might think of little who's on the speck of the dust that Horton heard. And for the record, that's copyrighted. So those of you out on iTunes, you won't see that. Thank you. But I only really put this in there to prove that I'm really cross-disciplinary, because as we all know, Horton's placed the speck of the dust with the who's on a clover, which is a plant, which is like a planet, except it lacks an E. The planet I've worked on for the last 4 Earth years, notice I use Earth years, is Mercury. And this is an artist concept of our spacecraft, Messenger. It's a large interdisciplinary team. That's a $500 million spacecraft mission. And these are accentuated views of Mercury, the 2 hemispheres, that have been stretched to bring out color differences. So, for example, the large reddish spot on the left hand of those images is the Caloris Basin, one of the largest impact structures in the solar system. So, really remarkable planet to work on. Now, even before we ever got to Mercury, we knew a thing or two about it. Most remarkably is this enormous core the planet has. If you're standing on the surface of Mercury, and I don't really recommend that, you're only 300 kilometers above the surface of the core, that large metallic blob in the center of the planet. In contrast, on Earth, you're more than 3,000 kilometers away from the core mantle boundary. So the core makes up something like 80% of the uncompressed mass of the planet. And there's almost no oxidized iron, think of it as no rust, on the surface of the planet. So this led scientists to come up with the idea that most of the silicate shell, the rocky part of the planet, had been stripped off early in the history of the solar system by a giant impact. Another body hit Mercury, knocking off most of the silicate shell. While this was mostly a physical model, it really led to strong geochemical predictions, most notably that it would be depleted in volatiles. Now, if you've ever heard the term volatile, you might think of something like water, the drop of water, or the Morton salt girl, not the girl herself, but salt containing sodium and chlorine, which are both volatile elements in our sense, and even sulfur, some nice crystals of sulfur down there. So this prediction would be that none of these elements should really be present on the surface of Mercury. And yet when we got to Mercury, this is what we call a Caltech diagram. It's something versus nothing. And the something is just a measure of sulfur. The higher you are up on the plot, the more sulfur there is, and the bar there is the planet Mercury. The solid dots are the Moon, Vesta, Mars, and the Earth, planetary bodies, all very depleted in sulfur. In contrast, Mercury has weight percents of sulfur across the entire surface of the planet. It's much more like chondrites, these primitive rocks. There's one up there, those millimeter-sized particles formed in the solar nebula, these sediments that came out of the solar system, the building blocks of planets. So very difficult to explain, but these high sulfur concentrations, combined with a lot of other geochemistry we got from the planet, really suggest that this model doesn't work. And so we had to come up with, as we're in orbit, and we've been in orbit now for 2 years around Mercury, an entirely new paradigm for the history of one of our 8 solar system family members. But fortunately, because we work at places like the Smithsonian, we get to do interesting things that people often don't care about. And one of those, when I first started working here, was I got really curious about how this rare group of meteorites, these white things called aubrites, enstatite meteorites, formed. And we think that they formed from a group of meteorites like the black stuff, enstatite chondrites. This is a breccia, a rock composed of bits of other rocks, which is why you see the fragments in there. So if you want to know how one thing formed by melting from another thing, the easiest way to do is melt that one thing. And so we did that. We put this that's a sealed silica tube at 1,450 degrees Celsius. That's about 2,600 degrees Fahrenheit for those of you that should not attempt this at home. And you take it, and you take 160 milligrams of it, and you make that little ball up there, the 160 milligram planet. And if you cut that in half, you see that there are 3 things in there. There's white metal, there's the bronzish-looking sulfide, and there's the grayish-looking silicate in there. And what's really remarkable is the way these phases exchange elements. Because there's almost no oxygen in this system, you get weird things going on. So you get things like silicon going from the silicates into the metal. You get sulfur going from the sulfides into the silicates, and you get things like magnesium and calcium, which normally are really happy in rocks on Earth, going into the sulfides. And so a really bright postdoc of mine named Tom Burbine, about 2 years later, a real eccentric guy, but really bright, said, what if these experiments actually reproduce the surface of Mercury? And sure enough, you go back to this plot, that the gray dot out there, melted EH, is almost a dead match for Mercury. Because those melts, those magmas, those lavas that would erupt on the surface contain weight percents of sulfur. And so he said, well, what would the 160 milligram planet experiments predict for Mercury? Low FeO, which we see, high magnesium and high sulfur, which we see, calcium and magnesium sulfides, we see those on the surface, and silicon, the stuff you make computer chips out of, in the core of the planet. It's really an upside down world where the light stuff is on the bottom and the heavy stuff is on the top. And so because we could do these experiments here, because we could chase our curiosity and couple those with the results of a $500 million spacecraft mission, we have the chance as a team, not an individual, to collectively build a new idea, a new paradigm for the origin of a whole other planet. Thank you. You're all just so stunned, you know. I would put up a cladogram of planets for you, but it wouldn't make any sense. How about back there in the middle?
Given the high sulfur content, are there some similarities, do you think, between Mercury and Io?
Oh yeah, the question was, given the high sulfur content, are they similar between Mercury and Io? That's a really good question. Io, you know, most of the volcanism there is tidally driven, but it's probably at some level the same kind of process, which is you're dredging up sulfur from deep and somehow moving it to the surface. There, it's probably the flexing of the planet. Here, it was actually, we think, the dissolution of the sulfur in the silicate melt. Io is a mostly sulfur surface. But yeah, it's an interesting case of moving sulfur around on the surface of planetary bodies.